topic is going to be the fundamental theorem of algebra, and we know this is going to be relating to polynomials, which is similar to what we were doing before. So we're going to want to make sure to remember all your stuff about polynomials, dividing polynomials, how to find roots of polynomials, the quadratic equation and stuff. So that's kind of the stuff we're going to be building off of today. So the fundamental theorem of algebra. Now, it says it's fundamental, and that means it's really important, and it is. So basically what the fundamental theorem of algebra says is that every non-constant polynomial has at least one complex root. So that means if you're drawing a polynomial, if it's not just a straight line, then it's going to have a root somewhere. So even a polynomial like this has a root. It's not going to be a real number line root. It's going to be like a complex root, but we're going to deal with that later. I guess first we're going to be dealing with polynomials with real roots, so it's going to be if it intersects the real line somewhere. So you're going to see it's going to intersect the x-axis if it has a real root. So first thing I want to say about this is that if you have a polynomial like, say, x squared plus x minus 6, then we can factor this polynomial, and factoring it gives us our roots. So factored, I've done this one already before, so it's not too bad. And you can also, if you have a polynomial that's a quadratic, you can always use the quadratic formula to find out what the roots are. And part of the deal here is that if you know what the roots are, you can also know what the factors are. Because all this means is that one of the roots is going to be 2, because at 2 minus 2 it's going to be 0, so the whole thing is going to be 0 because it's multiplied together. And here one of the roots is going to be negative 3. And that is a fundamental idea of polynomials, and it's part of the fundamental theorem of algebra, the fact that you can factor a polynomial into these little parts, and each one of them tells you what one of the roots is. And from here, I'm going to do an example that's kind of meant to show how you can use the fact that you can factor out one of the roots to get the other roots. So if you start with a cubic polynomial, say like x cubed plus 13x squared plus 39x plus 27, and if I tell you that one of the roots is going to be negative 1, that means that one of the factors of the polynomial, if you write it out as individual factors with each one just an x term and then plus or minus some number, if I tell you that one of the factors is negative 1, that means that we can divide out x plus 1, and we're going to get some even polynomial here, which is going to be, if you multiply this polynomial times x plus 1, you're going to get this. So if we find out the rest of the factors of this polynomial up here, which is going to be a quadratic, then we can find out all the factors of our polynomial and all of the roots. And when we have a quadratic, we know we can use the quadratic formula. And there is a cubic formula, but that one's really messy, and it's not generally worth it to memorize it. So if you have one of the factors and you have a cubic, you can get it to be a quadratic, and then from there you can finish finding out the rest of the roots. So I'm just going to do that here. We're going to do some division. So let's start out, this would be x squared, because x goes into x cubed, x squared times. So x cubed plus x squared. Subtract, those cancel out. This is 12x squared. Bring down the plus 39x. This goes in 12x times. And we're doing more polynomial division. And polynomial division is kind of an important concept. I guess mostly only if you're dealing with polynomials, although there's a lot of things that are polynomials. So knowing how to work with polynomials, dividing them and multiplying, adding, subtracting is useful. This should be minus. So 39 minus 12 is 27. X plus 27. So looks pretty good. It looks like we're going to get something that's kind of nice, and we should get 0 as our remainder, which makes sense. So 20x plus x goes into 27x 27 times. So 27 up here, 27x plus 27 minus, those cancel out, we get 0 as our remainder. Remainder 0. That makes sense. So that means that x plus 1 times this polynomial here is going to give us this, our cubic polynomial. So we can use the quadratic formula to find out what the rest of the factors are of this one, and then we'll have all of our factors and all of our roots for this cubic polynomial here. So we're just going to do that real quick. Do you guys remember what the quadratic formula is?
Yeah.
Okay.
Minus b
Negative plus or minus
Plus or minus square root
of b squared minus 4ac.
over 2a.
Yeah.
What is our thing? A is 1. Okay, I'm just going to plug that in here. Negative b, negative 12. Plus or minus 144 minus 4ac. 4 times 1 times 27. What is 4 times 27? That's like 108. Probably should have written it slightly. A reasonable number over 2a is over 2. Okay. So, it's just going to be, let's simplify this over here. So, it's negative 6 is negative 12 over 2, and plus or minus this thing over 2. 144 minus 108. Here's a calculator, I guess, if you can do that real quick. It should be like 36. Oh,
Oh, the on button is right there.
yeah.
AC.
So square root of 36
Oh, okay.
is 6. Negative 6 plus or minus 6 over 2, so negative 6 plus or minus 3. Okay, so what is this? Negative 6 plus or minus 3 is negative 9, and negative 3. So our roots there for our negative 9, negative 3, and negative 1, which means our cubic polynomial is going to factor out to be x plus 1, x plus 3, and x plus 9. And we can write it out in this form and we know what our factors are, or we can just write out what our roots are if we want to know where we want to look on the number line to figure out where it intersects. So that's one useful thing that you can do if you have just one factor of a cubic polynomial. You can reduce it to a quadratic and then from there finish solving it. So the next thing I want to talk about is how we can know how many factors our polynomial in total is going to have. So the fundamental theorem of algebra tells us that if we have any polynomial, just call it p of x, just use a random variable, so we don't have to list out like a0x plus a0 plus a1x plus a2x squared and whatnot. So if we have some polynomial x, then there's at least one root, and the fundamental theorem doesn't tell us that this root is necessarily going to be a real root, so we're going to have to consider complex numbers. So we know you're already a little bit familiar with complex numbers because the quadratic formula, if in here you get a negative number, you're going to be getting kind of a not quite real number, so it's going to have an imaginary part represented here and then the real part. And what this tells us is that the fundamental theorem is not always going to give us, well, the fundamental theorem doesn't give us the root, but it tells us that there is a root. So the root is not necessarily going to be a real root. So, like, that's a thing you have to consider with polynomials. And here, if you have some polynomial x, there's at least one real root r. And if you're dividing out by x minus r, as we can do because the polynomial is going to factor into its roots, And so if we divide out by x minus r polynomial, if it had degree n before, so let's say polynomial p of x with degree n, so it has some like its biggest term is going to be x to the n. And if we divide out by something with degree 1, what we're left with, we can call it q of x, like the quotient is what you generally say. So the quotient of p of x divided by q minus r is going to be some polynomial q of x with degree n minus 1. So we know that if we have something of degree n, we can find one root of it, and then we take that root out and we have something of degree n minus 1. And the fundamental theorem says is that if the degree is at least 1, then we can find a root. So if we keep going in this process, say divide out by the next root and then get something of degree n minus 2, we're eventually going to get to a constant, and by that time we'll have found n roots. So any polynomial of degree n is going to have n roots. And those roots can be complex, which is what the next part's going to be about. So if you just consider the polynomial like x squared plus 1, then you know that this doesn't intersect the real line at any place, but it intersects the complex line. So you can consider where this equals 0, and you know x squared is going to be equal to negative 1, and therefore x is going to have to be equal to the square, or plus or minus the square root of negative 1. So this is also what we like to call I, because it's simpler than writing out the square root of negative 1 all the time, but essentially all it is the square root of negative 1, and it can't be simplified into any real number, which is why it always has to be represented as something apart from the real numbers. So like as a term I. So these would be the roots of this polynomial here, and in general,
powering off.
Okay. In general, if you have a polynomial of degree, if you have a polynomial of degree n, you know it's going to have n roots, and that roots can be complex. But also, if you have a polynomial p of x, and you say one of its roots is r, if we're going to say that this root is complex, it can be written as a plus bi, where a is a real number and b times I is going to be the imaginary part of this number. Another root of this is also going to be a minus bi. So, I guess say r prime. Actually, no, I wouldn't say r prime. I'd say r dash, because that's the conjugate. So, the next thing I'm going to be talking about is complex numbers a little bit more in detail, and in particular about this guy right here. So, you know, you can always represent a complex number as a plus bi, where a and b are real numbers, and then bi is going to be the imaginary part. And a minus bi is what's known as the complex conjugate. So, you have r equals a plus bi, r with a line over it, which means the complex conjugate is going to be a minus bi. And what we want to show is that if we have some polynomial and we have a root r, a plus bi, then we want to show that a minus bi is also going to be a root of this polynomial. So what we do here is we write the polynomial out like expanded, kind of in abstract form. So it's going to be, you know, a0 plus a1x plus a2x squared, and so on, all the way to a n x to the n. And since we have here just a big bunch of terms added together, we can simplify this in summation notation. So I from 0 to n, a to the I, x to the I. And basically all this is it's putting each of these terms as its own piece indexed by I. So a0 is going to be when I equals 0. When I equals 0, we're going to have a0 and x to the 0. X to the 0 is 1. So that term would just be a0, x0. X is 0 equals 1, so that would just be a0, which is our term here. So we're just writing out each of these terms in kind of a compact form. And what we want to note here about these complex conjugates is that if we plug in r into this formula here, we know that that's, I do it separately, because this is like the general representation. We want to say a specific thing about it. So we know, because r is a root, that if we plug r in where x is, we get 0. And what we want to say is that if we plug in the conjugate of r, then we also get 0. So if we plug in the conjugate of r to the I, we also get 0. And what we want to do here is kind of utilize some of the properties of a complex conjugate. So here we've written out what a complex conjugate is, and from this definition there are a few properties of complex conjugates that you need to be able to work around. So if you have some r, then if we're multiplying the r by some real number a, the complex conjugate of a times the complex conjugate of r is going to be the same as a times r and the complex conjugate of that together. So what that allows us to do here, I have to do one more thing. So the complex conjugate of r to the m equals the complex conjugate of r to the m. And what is important there is just the grouping, which one you do first. So that means that you can switch the order between when you take the power of something and when you take the conjugate of it. So that means that we're going to be able to apply this conjugate across the whole part. One more thing. So if we have r plus r prime, it's just function, I would say s, r plus s, r, the complex conjugate of r plus the conjugate of s, is going to be the conjugate of r plus s. And so, since these are all added together and they're all complex numbers, we can chain that together in order to combine them all into one complex conjugate. So here, using this first, this second rule first, because we're dealing with this term, we're going to basically apply this across the whole thing, including r to the I. So r to the I conjugate is going to be equal to r conjugate to the I. So that gives us the sum a to I from 0 to n. R conjugate. And next we can see that due to the second rule, we can extend this across the whole thing. So our term inside, the conjugate of the whole thing, is equal to this. So next, this second rule, we see that what we have here is just a lot of additions repeated. This is telling us we can do this with just one, but if we can do it with 1 and combine 1 to 2, then combine 2 into 3 and 3 into 4 and so. So this, we can apply the complex conjugate of the whole thing. And what we have now is that we have what we had originally, but just the conjugate of it. And so next, what we want to see is that 0, the complex conjugate of 0 is just 0. So we go back to the original definition to find out what the heck that means. So we've written our complex number in separated form. So 0 is just going to be 0 plus 0i, because, well, you know, that's how 0 is. And so the complex conjugate of this can be 0 minus 0i. But 0i is just 0, so that's equal to 0 anyway. So the complex conjugate of 0 is equal to 0 itself. So we know that this thing inside is the same as this, which is 0. So this is the complex conjugate of 0, which is just 0. So therefore, if we plug in the complex conjugate of r, we also get 0. That's might be kind of hard to follow, but it's not necessarily for you to exactly follow all of it. But all you have to remember is that if one of the roots of the polynomial is a plus bi, another one's going to be a minus bi. So that means like if you have a, let's say, a polynomial of degree 3, any degree 3, 2 to the 3. So if you have some polynomial of degree 3, you know by the fundamental theorem of algebra that it has at least one root. And you know that if that root is going to have b where, well, it's going to have, is going to be a complex number. If it's going to have an actual and imaginary part, then it also has to have a pair that goes along with it. So for odd degree polynomials, this means that since you have to have pairs of complex roots, that you have to have at least one real root, because the real root doesn't have to have a pair. And so essentially you have where the number of complex roots you can have is going to be some multiple of 2. So it's going to be like 2 times k. And then for a polynomial of odd degree, you have to have at least one real root, because you have to have one that doesn't have a pair with it. So that means, all that means is kind of confirming like what you already know. So like if you have a polynomial of degree 3, I'm going to erase something. If you're drawing out any polynomial of odd degree on a number line, you know it's, well, you know it goes to infinity in one direction and negative infinity to the other, so it might do some crazy stuff. Actually, that's not a function at all. I can't be doing that. So, you know, it's might be doing some stuff in the middle, but at some point it's going to have to cross the line. All that means is that it has at least one real root, which is what this was showing. So that's how that's derived. So if you know the fundamental theorem of algebra, and you want to work with some complex numbers, then you can show that you have at least one real root of any polynomial of odd degree. So any polynomial of odd degree has at least one real root. Because, you know, there's at least one point where it crosses the x-axis, and that's obviously going to be a real number because it's on the real number line. At least one real root. And that's not necessarily true of even degree polynomials. Like an even degree polynomial can have real roots aplenty. It can have as many as it wants, but it can also have none. It can just be all the way up above or all the way below the x-axis. At least one real root. And so the basic things to take away from this are going to be that any polynomial of odd degree has at least one real root. If you have a complex root of a polynomial, say a plus bi, you know you also have a minus bi. Because they come in pairs. And if you have a root of a polynomial, you can divide, well, you can factor out that root, you can divide it from the original polynomial. So if you have some polynomial p of x, and one of the roots is r, you can take p of x and divide it by x minus r. And that'll simplify it into a polynomial of one less degree. And so if you have a root, you can reduce your polynomial. So if you have a cubic, and you have one of the roots you can divide out that root and find the quadratic, and then from the quadratic, you can use the quadratic formula to finish solving out the rest of the roots. So that's essentially the 3 takeaways from this lesson. Okay, are there any questions?